In this lecture, we'll be continuing with the quotient group. So first we'll be defining properly discontinuous action. So we'll prove that a group is quotient if and only if it acts properly discontinuously on the hyperbolic plane. We'll be also proving that a group is quotient if and only if its orbit is discrete. So let us begin. Okay, so first we'll define properly discontinuous action. So let G be a group. So G be a group acting on a topological space, or in fact, I'll take it to be metric space. Okay, so let us take topological space. So in fact, one can take it to be metric space also. So we say that G acts properly discontinuously on X. So if for all compact sets K subset of X, so the set, so you take this set, so take all those elements G in this group, capital G, such that, so you have an action of this group on the space X. So G of K, it makes sense. So you intersect GK with K if it is non-empty. So you take all the collection of this G such that GK intersection K is non-empty. So this is finite. So this is my definition of properly discontinuous action. So here, yeah, so in order to define properly discontinuous action, so you do not need to be this topological space to be metric space. Okay, so now let us try to understand this action with the help of examples. Okay, so so let us take this action of Zn on, so the action of Zn on Rn is just by the translation. So this is my action. So this is just translation. So one can check that. So this action is, so the above action is for instance, if I take n equals to 1, so if I take n equals to 1, and if I take K to be a compact set of, so K is a compact set of this R, so then K will be contained in some closed bounded interval AB. And now if I take this real line, and suppose this is my closed interval AB. So if I consider the set, so n belongs to Z such that the closed interval intersection AB intersect with this translate of AB, n plus AB, it is just the translate of interval AB. So this intersection is non-empty. So suppose I take this thing, so this intersection, so intersect AB with the with this translate of this closed interval AB. So this intersection is non-empty. So only for finitely many n's. So this is very easy to see. So you'll get only finitely many overlaps of the translates of this AB with the closed interval AB. So therefore, so this set is a finite set. So cardinality of this set is finite. Yeah. So this you can extend for n greater than 1 also. So therefore, this Zn, it is acting on Rn by properly discontinuous action. So let me give you one non-example. So let alpha be an irrational number. And suppose if I take this action, so so Z is acting on S1 in the following way. So any point of S1, you can write it as e to the power 2 pi I theta. So the action is, or the mapping is e to the power 2 pi I n times theta plus alpha. So if theta is equal to 0, so the set e to the power 2 pi I n alpha, where n belongs to Z. So this is, one can prove that, so this is dense in the unit circle S1. Yeah, so therefore, so this action of Z on S1 will be not a properly discontinuous action. So this requires a proof. Okay, so now let me come to this theorem. So let gamma be a subgroup of this PSL to R. So then, so this gamma is a Gaussian group if and only if gamma acts properly discontinuously on upper half plane. So what is the proof of this thing? So suppose gamma is a Gaussian group. So what we want to prove that gamma acts properly discontinuously on this upper half plane. So suppose gamma does not act properly discontinuously on upper half plane, we will arrive at a contradiction. So if possible, let gamma does not act properly discontinuously on upper half plane. So then it means that, so then there exists a compact set K in H2 such that, so this collection so G belongs to gamma, so GK intersection K non-empty is infinite. So this means that so because this is infinite, so there exists a distinct sequence sequence Gn. Let me write in this way. So distinct sequence Gn in E. Yeah. So now because this Gn it belongs to E, so Gn K intersection K is non-empty. So implies so there exists this Xn belongs to K and Xn also belongs to your. Yeah, so one can prove that. So Gn of Xn it belongs to your K also. Yeah. So how do you prove this thing? So suppose Yn belongs to K intersection Gnk. So then Yn belongs to K and Yn it belongs to your Gnk. Because Yn belongs to Gnk, so there exists Xn belongs to K such that Yn is equal to Gn of Xn. Yeah, so therefore we have this thing. So Xn belongs to K and Gnxn also belongs to K. Okay, so we have this thing here. So because K is compact, so K compact, so this implies that K is also closed and bounded. So therefore, so there will exist a subsequence of Xn which will converge to a point in K. So without loss of identity, what we can assume? So this Xn converges to X in K. And same thing we can do for Gn, the sequence Gn Xn. And also without loss of identity, I can assume that Gn Xn, it converges to some point Y. So where this Y, it belongs to K. So also note that this X also, it belongs to your K. So now let us take some epsilon greater than 0. So then for all large n, so d distance between hyperbolic distance between xn and because xn converges to x, so this distance will be less than epsilon for all large n. Now we know that this Gn is this isometry of this upper half plane. So this will imply that so Gnxn G so distance between Gnxn and Gnx, again it is less than epsilon because Gn it is an isometry. Okay, so I can take it to be epsilon by 2. Let us take it to be epsilon by 2. Also Gnxn it converges to y. So for all large n, so the hyperbolic distance between Gnxn and y, so this will be also less than epsilon by 2. Yeah, so now if I apply the triangle inequality, so for all large n, so what we have, so for all large n, so we have this thing, the hyperbolic distance between Gnx and y is less than equal to this distance plus this distance. So we have this thing less than equals to that thing, and those two distances are less than epsilon by 2. So therefore what we have, so this distance is less than epsilon by 2 plus epsilon by 2, which is equal to your epsilon. And this is true for all large n. So what we have proved that this g and x, it converges to your y. Okay, so now if I take this this closed ball, so let us take this closed ball around this y. So because g and x converges to y, so there exists. So take this ball. So there exists a natural number such that so g and x will belong to this closed ball for all n greater than equals to n naught. So you have this thing. And also note that, so this is a compact set in the upper half plane. Because this is closed and bounded, so this is a compact set in the upper half plane. Now let us take some m greater than equals to n naught. So gmx, so this is equal to gm g n naught inverse g n naught of x. So we know that gmx, it belongs to the closed ball. So therefore, so this will belong to the closed ball around this y, and the radius of that closed ball is epsilon. Yeah. Okay. So also observe that. So this sequence, now I am adding this m. So m is greater than equals to n naught. So this sequence is an, so where this m is greater than n naught is an infinite sequence. And so this sequence, it is a subset of the set. So T belongs to your gamma such that T of this Gn naught x, it belongs to your this closed ball. So now observe that this closure of this ball, so closure of this ball, so this is compact, and so T is varying in this gamma, and T of some point, it belongs to this compact set, B bar. So in the last class, we have proved that, so in the last class, what we have proved that uh, this set is compact. So this set is compact, and we have assumed that gamma is Gaussian. So this means that gamma is discrete also. So gamma is discrete in this PSL to R. And from the previous class, so this set is compact in PSL to R. So this compact plus discrete will imply that, so the above set, so let us call it to be capital A. The set A is finite. Okay, so this proves that, so uh, so the sequence, it is a finite sequence, is a finite set. So therefore, so this sequence is not an infinite sequence. So therefore, so we have a contradiction. So we have a contradiction, and the contradiction is due to the assumption that gamma does not act properly discontinuously on the upper half plane. So this proves that, so gamma acts properly discontinuously on the upper half plane. Now let us prove the converse part. So conversely, so what we are assuming, so let gamma acts properly discontinuously on upper half plane. So then what we want to prove, uh, so the claim is, so gamma is discrete in PSL to R. Okay, so suppose not. So then there exists a distinct sequence distinct infinite sequence Tn of gamma such that, so this Tn, it converges uh, to T, where this T, it belongs to your PSL to R. So now let us take some point. So let x naught belongs to your upper half plane. So Tn of x naught, it converges to your Tn x naught. So this convergence, Tn converges to T pointwise. Okay. So now if I take a ball around, so this is a closed ball. So closed ball around. So this means that x belongs to your upper half plane such that the hyperbolic distance between x and x naught is less than equals to r. So this proves that, so there exists, so t and x naught converges to your, sorry, t x naught. So there exists n naught, some natural number n naught, such that, so this Tn x naught, it belongs to your T of this translate of this ball, which is nothing but again equal to, because T is an isometry, it is again equal to the closed ball around Tx naught. of radius r. So let us take this to be K, say. So K is a compact set in this upper half plane. So now if I take, so let n greater than equals to n naught. So Tn x naught, so this is equal to your Tn naught inverse of Tn naught x naught. So Tn x naught, it belongs to K. So this belongs to your K. So this proves that, so this proves the following. So also note that T n naught x naught, it belongs to your K. So therefore it proves that, so Tn naught inverse of K intersect with K. So this is non-empty for all n greater than equals to n naught. So this proves the following. So so this will imply that, so the set S belongs to gamma such that you apply S on so you take the translate Sk and intersect with K. So this intersection is non-empty. So this collection of S is infinite. So this contradicts that gamma acts properly discontinuously on upper half plane. Okay, so we have proved this theorem. So what we have proved that gamma acts properly discontinuously on upper half plane if and only if gamma is a Fauchian group. And the next theorem is, so let us take gamma to be a subgroup of this PSL to R. So gamma acts properly discontinuously on upper half plane if and only if for all z belongs to your upper half plane. So the orbit, so gamma dot z, so this is the collection of all CZ where this G is varying in this gamma. It is a discrete subset of this upper half plane. So again, the proof is done in the similar way. So let us first assume that, so let gamma acts properly discontinuously on this upper half plane. So if, so this is not discrete for some set in upper half plane, so then there exists an infinite sequence, in fact distinct sequence Gn of gamma such that, so Gn applied on Z is converging to some W belongs to your upper half plane. And now let us take K to be this closed ball, some closed ball around this W, and the radius of this closed ball is epsilon. So where this epsilon is a positive number. So again, so there exists some natural number n such that so Gn z it belongs to your k for all n greater than equals to n naught. So now Gn naught of z it belongs to your k, and again by this observation, so Gnz is equal to Gn naught inverse of Gn naught z. So this again it belongs to k because Gn z belongs to k. So this will prove that so Gn naught inverse of k intersection k non-empty is non-empty for all n greater than equals to n naught. So this proves that so so this whole uh, sequence, so this is contained in the set. So because so this is an infinite sequence, so this will be an infinite set. So this proves that so gamma does not act properly discontinuously on this upper half plane. So which is a contradiction. Because we have assumed that this gamma is acting on this upper half plane properly discontinuously. And converse part I'll leave as an exercise. So the proof will be done in the similar way.